Welcome to The Explainer. I am absolutely thrilled to have you here today because we are venturing into the genuinely fascinating world of orbital mechanics. Look, we rely on satellite imagery for almost everything in our modern world, right? From tracking massive weather systems to monitoring global crop health. But have you ever stopped to wonder how we actually achieve such perfect, consistent imagery day after day? Well, today, we are unpacking exactly how the brightest minds in engineering pull off this incredible feat.
To kick things off, I want to pose a bit of a mystery for you. How do we accurately track climate change from space without shadows getting in the way? Think about it. The Earth is constantly spinning, it's constantly orbiting the sun, and the lighting changes literally every single second. If you're a scientist trying to measure subtle, long-term shifts in deforestation or shrinking ice caps, constantly shifting shadows would create a chaotic, totally unusable mess of data. So how on Earth, or rather above Earth, do engineers solve this massive lighting problem from hundreds of kilometers up in space? Okay, let's dive into this by using a really simple, intuitive analogy. Imagine you want to track the changing seasons by taking a photograph of your own house every single day. If you take that photo at exactly 10:30 a.m. every day, the sunlight and the shadows on your porch are going to look very similar. That consistency makes it incredibly easy to detect real physical changes, like a new tree growing in the yard, or maybe some new construction. But if you take those photos at random times, say dawn on Monday, noon on Tuesday, and dusk on Wednesday, the wild differences in the shadows will completely obscure the actual changes to the property. It would just look like a mess of shifting light.
All right, here's our roadmap for today's explainer. First, the daily photo analogy. Second, defining sun-synchronous orbits. Third, the mechanics and physics. Fourth, sun-synchronous versus geostationary. And fifth, real-world satellite missions.
Section 1. The daily photo analogy.
So take that house analogy and scale it up to a multi-billion-dollar satellite. Constant lighting matters immensely. When you have a constant local solar time, shadows remain nearly identical day after day. The illumination angle hitting the Earth's surface is totally consistent. What this means is that temporal comparisons, say comparing an image from 5 years ago to an image taken today, are incredibly reliable. Because we've entirely eliminated the lighting variables, any seasonal or physical changes we observe are isolated. We know for sure we're looking at real change, not just a trick of the light.
Moving right along to Section 2. Defining sun-synchronous orbits.
A sun-synchronous orbit, or SSO for short, is defined as a special type of near-polar orbit where a satellite passes over the same location on Earth at approximately the same local solar time every day. Now, this is the magic sentence right here. Because it hits that exact same local solar time, the sun's position in the sky is nearly identical for every single pass over the Earth. It essentially locks the lighting conditions in place for the satellite's cameras. Let's look at the hard spatial facts that actually make this possible. SSOs operate at an altitude between 500 and 900 kilometers above the Earth. They have an orbital period of about 95 to 105 minutes. That means they are flying incredibly fast, completing roughly 14 to 15 full orbits around the planet every single day. And, most importantly, they maintain a fixed local crossing time. So a satellite might be designed to always cross the equator heading south at exactly 10:30 a.m. local time without fail.
Now, what's really fascinating here is that inclination number we just mentioned, between 96 and 99 degrees. An inclination greater than 90 degrees makes this a retrograde orbit. That basically means the satellite is actually flying slightly against the direction of Earth's rotation. Why would we ever want to do that? Well, as we're about to see, that specific retrograde angle is mathematically necessary to force the satellite's orbital plane to drift, or precess, eastward at the exact rate we need.
Which brings us to Section 3. The mechanics and physics.
It all comes down to planetary physics. Step 1 reveals a pretty fun fact. The Earth is absolutely not a perfect sphere. Because it's constantly spinning, it actually has a bit of a muffin top. It bulges at the equator and flattens at the poles, making it an oblate spheroid. Because of this extra mass around the equator, Step 2 kicks in. Earth's gravity pulls on the satellite unevenly. This specific gravitational tweak is known in physics as the J2 effect, or the J2 perturbation. And Step 3 shows the result of that pull. This uneven gravity gradually rotates or precesses the satellite's entire orbital plane eastward.
Now we need to perfectly match that drift to the Earth's movement. Let's do a little math, but I promise it's easy. The Earth moves about 360 degrees around the Sun in 1 year, specifically 365.2422 days. If you divide 360 by 365.2422, you get exactly 0.9856 degrees per day. For a Sun's synchronous orbit to work, engineers must design the orbit so that the natural J2 drift we just talked about matches this exact number. If the orbital plane precesses at exactly 0.9856 degrees per day, the angle between the orbital plane and the Sun literally never changes. It is perfectly synced.
When we look at the actual physics variables of that nodal precession, things like the rate of ROA and change, Earth equatorial radius, and mean motion, it looks like a ton of intense rocket science, and honestly, it kind of is. But I want to draw your attention to just two of these variables, the semi-major axis, which is essentially the altitude, and the inclination. So the crucial takeaway here is that out of all this complex math, engineers really only need to select and tweak the altitude and the inclination. By balancing just those two factors, they can hit that magical 0.9856-degree target to seamlessly match the Earth's revolution around the Sun.
And this brilliantly illustrates the final payoff of all that math. Imagine a satellite perfectly designed for a 10:30 a.m. descending node orbit. Whether it is January 1st, April 1st, July 1st, or October 1st, every single time that satellite crosses the equator heading south, it does so at approximately 10:30 a.m. local solar time. The Sun's position is exactly the same all year round, even as the satellite flies over completely different longitudes on every single pass.
Let's move on to Section 4, Sun synchronous versus geostationary.
When we put these side by side, you can really see how specialized this is. SSOs sit very low, at 500 to 900 kilometers, with a nearly 98-degree inclination, scanning the whole globe every few days with that constant solar time we talked about. Now, compare that to a geostationary orbit. Those sit all the way out at nearly 35,800 kilometers away, right over the equator at a 0-degree inclination. Geostationary satellites don't scan the globe, they just stare continuously at one fixed region. That makes them absolutely fantastic for live communications and weather monitoring, but pretty terrible for taking close-up, consistently lit, global before and after photos.
Finally, Section 5, real-world satellite missions.
Because SSOs provide such reliable, highly comparable data, they're the absolute backbone for critical global industries. We're talking about Earth observation, vital environmental monitoring, and tracking agriculture to ensure our food security. It's also the essential orbit for climate studies, precise mapping, and disaster response. Think about it. When a natural disaster strikes, first responders need clear, comparable images to see exactly what has been destroyed versus what was there just yesterday. SSOs guarantee that weird shadows won't confuse that critical assessment.
And these are the famous mechanical workhorses actually doing this job above our heads right now. Most Earth observation satellites utilize SSOs. You've got Landsat 8 doing incredible land imaging and environmental monitoring. There's Sentinel-2 tracking our agriculture and vegetation cover. The Terra satellite is up there constantly monitoring our climate and atmosphere, while Worldview 3 provides the high-resolution, commercial imagery that you might literally see on your everyday smartphone mapping apps. All of them are riding that J2 gravitational wave to keep the lighting completely consistent.
Which brings me to a final thought I really want to leave you with today. If engineers hadn't figured out how to harness this bizarre quirk of physics, if they didn't utilize the J2 effect caused by Earth's slightly flattened poles to achieve constant lighting, how far behind would our understanding of global climate change be today? Think about that the next time you see a satellite image of our beautiful, changing planet. It's not just a camera in space, it is an absolute masterpiece of orbital physics. Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll catch you next time.